Una disculpa, perdón. Él es también director de investigación del Centro para Geociencias, Petróleo e Ingeniería de la Universidad de Leeds, y también es el encargado del laboratorio Wolfson de flujo multifásico. Así que vamos a recibirlos con la conferencia que ellos tienen para el día de hoy.
So thank you. I'm not going to talk about anything technical in my talk. I'm just going to tell you a little bit about Leeds. Perfect. Does that work? Yeah, so I'm just going to tell you a little bit about Leeds. And firstly, I want to say thank you to everyone at UNAM and Tampico for inviting us here. So we've quite recently started our collaboration, and so we've had multiple visits between Leeds and Mexico. I'm looking at Alejandro here because he's helped us a lot, and Jonathan, and we had Jose and Nancy in Leeds a couple of weeks ago. So I lead a centre at Leeds called Petroleum Leeds. So as the name would suggest, we are a group of academics who are all working on problems that are associated with the oil and gas industry. Does this work? Yes. So I'm just going to give you a brief overview of the university, where it is, because a lot of people don't know where Leeds is. We don't have such a good football team as Manchester United or Manchester City, so no one ever knows where it is. It's actually the third largest city in Leeds. It's actually the third largest city in the UK. It's in the north of England. I think this has got other names on it. So you can see we're pretty close to Manchester, and Sheffield apparently is the centre of the universe, but we won't talk about that. 2 hours on the train from London. I'm not going to dwell too much on this because I want to hand over to Quentin so he can talk about the research that we're doing, but this is the campus. We're very close to the city centre. Leeds is a much smaller city than, say, Mexico City, so you can pretty much walk around all of it. In terms of the university itself, it's one of the research-intensive universities in the UK, which is a group of universities called the Russell Group. We're the third largest organisation in that group, and it's a pretty big campus in terms of UK universities, with 35,000 students and over 7,000 staff. We're in the top 100 universities in the world, and we were the University of the Year in 2017 in a UK context, so that was great for us. We have lots of international students at Leeds and international staff, so we have a very outward-looking focus for our activities, and we're part of lots of global partnerships and networks, and our relationship with UNAM and Tampico is part of that strategy as a university to work with partners across the world. At the moment, we're investing heavily in our campus. We've got a big investment into engineering and physical sciences, so we are bringing all of that activity into one place, and we have a big new materials science research centre called the Bragg Centre associated with that, and that's being built at the moment, so it's actually just a big hole in the ground right now, but it's going up quite quickly. So the campus itself is great. There's lots of opportunities for researchers and also students in terms of access to world-class facilities, and that feeds into our research. 83% of that has been rated as world leading or internationally excellent. That's an exercise we go through in the UK every 5 or 6 years to assess how well we're performing. The other thing that we're very good at is our applied research, and that's kind of demonstrated from the fact that we spin out our research into commercial organisations, and Quentin will tell you a little bit more about one of those in a minute. So in terms of the centre, we cover geology, geophysics, kind of all the geoscience disciplines, engineering, and also sustainability research within the centre. So we're very interdisciplinary, and the centre provides a home for maybe 35 staff across campus, and we have an active research community as well in terms of postdoctoral researchers and PhD students. Most of that activity is funded by companies. We have relationships with over 30 different oil and gas companies, and they directly fund our research within the centre. So in terms of what we do in engineering, we have a lot of expertise in corrosion and flow assurance and scaling problems, and this is all homed within our School of Mechanical Engineering. And the visit from UNAM and Tampico last month or a couple of months ago, we were able to facilitate meetings between the academics from here with our academics in Leeds in this area, and also in particle science. And this is the school where Jose and Nancy came to visit a couple of weeks ago. So everything we do, we're focusing on the fundamental research, but also with an eye on how we can apply that. So some of the applications you can see at the bottom, things that I'm sure that you'll be familiar with and we've already heard about today, so enhanced oil recovery, and reservoir characterization. So this is activity that goes on in two schools in our university. One is within the School of Mechanical Engineering, and one is within the School of Chemical and Process Engineering. So this is the function here of Petroleum Leeds, is that we bring those activities that happen in different schools together, and we work together. So that's part of the ethos of the centre. And then if we move on to geoscience research, I'm not going to talk too much about the thing at the bottom, because Quentin's going to talk to you about this. But a lot of the research is focused on reservoir characterization and understanding the host rocks of the oil and gas, just to in terms of things like sedimentology and basins and structural geology. So we're looking at that in both an exploration and a production context. But you'll also see that because of the way that we structure our research, we're interested in some of the other applications of this research. So with the way that things are kind of changing, especially in the UK, there's a move away from oil and gas. So we do that alongside looking at things like nuclear, CCS, and even offshore infrastructure such as wind farms. So I'm going to hand over to Quentin, because he's going to talk about the research that's much more relevant to this conference. But thanks a lot for listening.
Good afternoon, everyone. What I'm just going to do today is talk about some of the research that we do in petroleum engineering and geoscience. I'm not going to give a lot of results. What I thought I'd do is just quickly go through all the different areas we work on. And then if any of you want to collaborate with me, you can just get in contact with me through my email. In the UK, Quentin is a really rare name, so if any of you Google me, you'll find me dead easy. Yeah. But before I start about our research, I thought I'd just say something about the energy landscape in the UK. You know, yesterday we had a few talks on energy in Chile, in Mexico. So in the UK, for the last 200 years, we've produced a lot of coal, and we're quite self-sufficient in terms of energy. And then in about 1980, we really started to get a lot of production from the North Sea in terms of oil and gas. And over much of that time, until 2005, the UK was independent in terms of oil and gas. We didn't really need to import very much. But over the last 10 years, the North Sea reserves have started to diminish, and now we're needing to import quite a lot of oil and gas. The other thing that's happened in the UK is that we've made a commitment to reduce our greenhouse gas emissions from about 80% of the level of the production in 1990 by the year 2005. And so we've made a big investment in renewables. For instance, now something like 25% of our electricity comes from renewables. But to get to this 80% reduction, we're going to have to do a lot more work. So we're going to have to invest a lot in terms of things like carbon capture and storage. We need to increase renewables a lot more. But during that time, we're going to also be using a lot of gas. And so some of the key challenges that we have at the moment are, firstly, we want to maximise the amount of fossil fuels that we get from the North Sea and from onshore UK. We want to develop carbon capture and storage technology, and we really want to increase the use of fossil fuels. So what I'm going to talk about now is some of the ways that we're trying to achieve those goals within our group. So the group that I work with, we can generally say that it's called petroleum geoengineering. And what I mean by that is that we try to integrate all the different geoscience disciplines with other disciplines such as scientific computing, statistics, geochemistry, petroleum engineering. And it's something I think I've found over the past 30 years working in the petroleum industry, that any problems that you get in the petroleum industry, if you integrate these different skills, you tend to get very original and good solutions. So most of the projects I'll talk about today, we really try to integrate all of these different disciplines to arrive at a good solution. So in terms of the projects that I do, probably about 80% of the projects that I do what we call joint industry projects. That's where, say, we'll get 6 different oil companies to sponsor them. And so I'm going to talk about quite a few of these today. But we also, we really try to get our research results used by industry very quickly. So one thing we do is a lot of consultancy work. So probably about 25-30% of my time is spent consulting. And we also do a lot of things like software development, just so that the petroleum industry gets our results very quickly. Yeah, we've got a lot of oil company sponsors. I can't remember how many are on here. I can't remember. A lot. So something like 30 different oil companies sponsor our work at the moment. We've got very good laboratory facilities. Carlos has already talked about these at the moment, but certainly in my field and the work that Carlos has done, we've built very good laboratories for working on particularly low permeability material. We've also got really state-of-the-art electron microscopy and imaging facilities. So we've got a big range of scanning electron microscopes. We've got focused ion beam, FIB. We've got really good transmission electron microscopes. We've got various CT scanners. In my laboratory, we've got a medical CT scanner, but we've also got a micro CT scanner elsewhere. So what I'm going to do now is just talk about some of the recent projects that I've done, that we've done. We've got a lot of them going at the moment, so I can only talk about a few of them. The first one that I'll talk about a little bit about is some work we've been doing on tight gas sandstone reservoirs. So I think someone gave a talk yesterday about how a lot of the conventional reservoirs have been depleted within Chile, and exactly the same things happened in the UK. All of our conventional gas fields have pretty much been depleted, and so all that we're left with is very, very low permeability reservoirs. And so we've had a big project over the last 10 years. It's been about $5 million investment to try to better understand the petrophysical properties of tight gas sandstone reservoirs. So one thing that we've built is a really big database of the properties of very low permeability sandstones. So all our oil company sponsors have given us samples, and we've done this really detailed sample analysis. So for every sample we measure porosity, stress versus permeability, brine permeability, electrical resistivity, nuclear magnetic resonance, T2 distributions, mercury injection, ultrasonic properties. We look at their mineralogy, their microstructure, their surface area. And then about a third of those, we do this what we call special core analysis, where we do things like what Carlos talked about earlier, relative permeability, capillary pressure measurements, etc. And then what we do is try to integrate that with wireline log data. So when anyone drills a well, they lower a lot of tools down the well to make measurements. And we try to integrate this data so we can predict flow properties a little better. And to help us do that, we've created our own it's sort of data visualization and data mining software, which I'll show you a little bit now. So when we collect all of this, we collect a lot of image data, and we collect a lot of petrophysical property data. And we've created our own, it's a software tool called PetMiner, where which allows us to visualize the data and create a better understanding of the properties. So this is me in my room with this is my computer screen, which is about nearly as big as this one. It's very, very high resolution. And what the computer software allows us to do, instead of having pointers on the graphs, we have things like SEM, micrographs, CT images. We can plot data in multi-dimensional space, so we can do X, Y, Z plots, color plots according to different fourth property, make the size according to a fifth property. We've got really flexible data filtering. But this is a really key thing that we can do, is that instead of having a point on the graph, we put things like CT scans, backscattered electron images. And what this is really good at doing is allowing us to really understand what controls the basic properties of rocks. The software tool also has basic image analysis functions, and we're just building in data mining and machine learning functionality. And one of the things that a really key thing what we want to do here is to really cut costs for the petroleum industry. So if someone brings a sample to me that we've never analysed before, we can just make one or two really basic measurements, put it through this machine learning code, and identify what the analogues are on the database that we've got. And I'll give you an example of that earlier. So instead of a company having to spend, say, £2 million drilling a piece of core, and then spend a year analysing the core, often within about 6 hours, we can just get a piece of their rock from cuttings and estimate what their properties are. And we can save millions of pounds and a lot of time, and I'll try to show you examples of that. But what this software allows us to do is really start to look at what controls the key properties of rocks. So for instance, this is something, these are the electrical properties of rocks, and there's been a big controversy in industry that when you get low porosity rocks, companies like Shell thought that you'd get an increase in this thing that's called the cementation exponent. Whereas a lot of our laboratory measurements suggest entirely the opposite is happening. And what's really good about this is by using the software and imposing the images on the points, we straight away realise what the key controls are. And actually both are correct. You know, Shell's models was correct and our model's correct, but for different situations. So if you've got these very low cementation exponents, what we find is the rock's full of fractures. If you get these very high cementation exponents at low porosity, we find it's full of secondary or non-connected porosity. So just by relating the images to the data, that we can very quickly understand what their properties are. Another example of this is ultrasonic velocities. This is really important for understanding seismic properties. And what you can see here is a graph of porosity versus ultrasonic porosity. There's a massive amount of scatter on that, and it was there's a really poor understanding of what controlled the scatter on these plots. But what we did, we just plotted the CT scans on there, the electron micrographs, and straight away we just understood what are the key controls. So all the things with very high velocities tend to have this layering that's perpendicular to the parallel to the core plug. Points down here tend to have layering that's parallel. We often found things that were points over here had a lot of secondary porosity. So again, just by relating the images to the data, we could understand the key controls. So one thing that I want to quickly talk about is this is where we're doing a lot of work, and I'm spending a lot of time working with industry at the moment, is that when you drill a well, that it's really easy to measure the porosity down the well. But if you want to know if it's going to be economic, what you need is the flow rate. You need something called permeability. And what you can see on this graph, for any porosity, there's 5 orders of magnitude variation in permeability. And so really what the oil industry wants to do is be able to find out if their reservoirs up here, they make lots and lots of money. if the reservoir's down here, they might as well abandon it. They're never going to produce at economic rates. And so what we did, we just replaced all the data points with images. We found out exactly what was controlling the scatter. And one of the really big things was a lot of the rocks have clay in them. And some of the clay occurs within the pore space. Other coats the clay grains, and that really reduces permeability, whereas others don't have any clay in them at all. And if you look on terms of porosity permeability space, these different rock types have different positions in porosity permeability. So basically, by just looking at the microstructure of the rock, I can instantly tell if it's going to have permeability down here, really good permeability, or something in between. And then we've used things like machine learning, etc., to make this even more sophisticated. So for one particular rock type, we can tell if the this is all with grain coating clay. We can tell if it's got really, really bad permeability, so these reservoirs won't produce. Something that's intermediate permeability here, that they will produce at a reasonable rate, or something over here that produce at very, very good rates, just by looking at the microstructure. And once we know what this relationship between porosity and permeability is, we can just go to wireline log data. We can interpret the porosity, the saturation, and then we can apply these relationships that we've obtained just by looking at the microstructure to estimate what the something called the permeability height function in the reservoir is. And we can do this just based on little pieces of cuttings that come up from a well bore with the drilling mud. So we can save millions of pounds. We don't need to actually drill and take these big cores that are really expensive. And we can perform this analysis in something like 6 to 12 hours very quickly. And once we get the KH value, we can use simple, this is a simple radial diffusivity equation, to calculate what the flow rates in those reservoirs are going to be. And that's something that we've been very successful at over the last 2 or 3 years. And most of the companies that are producing gas in the UK and the Netherlands are employing this technology at the moment. So another big project that we've been doing is looking at shale permeability. So I think many of you know that shale gas, shale resource plays in the America have totally revolutionized the oil and gas industry. I think now, just this week, America took over from Saudi Arabia as being the biggest oil producer in the world. And the reason is because of these shale gas resource plays. But the problem is, there's not very good methods in industry for actually measuring their properties in the laboratory. For instance, we gave 6 different samples to different service companies in the oil industry. And what we found out is that their porosity values that they gave us back for the same sample varied by 300%. And the permeability values that they gave us back varied by 4 orders of magnitude between the companies. So even though we make a lot of money out of these reservoirs, no one can actually measure their properties in the lab very well, or couldn't. So we established a joint industry project sponsored by 3 of the major gas producers to develop new techniques and new computer software to be able to measure those properties. What's difficult about it, when you deal with shale, they've got very, very small pore spaces. And so a lot of the talks earlier have been about permeability. When you've got shales, because the size of the gas molecules within them is very close to the pore size, you get a lot of different gas flow mechanisms. So instead of it being controlled by continuum Darcy flow, you get gas flow mechanisms such as gas slippage, transitional flow, and Newton diffusion. And you have to take these different gas flow properties into account when you're interpreting laboratory experiments. And so what we've done is to develop a whole lot of new different types of laboratory experiment. And these are all transient experiments. So you're just looking at how the pressure changes as a function of time. And then we've developed a lot of things like finite elements and finite volume codes linked to mathematical inversion systems so that we can invert these pressure transient data into things like permeability, into the factors that affect Newton diffusion, etc. So this project's really, from what we can see, really improved the way that oil companies and gas companies can measure gas flow in shales. The other thing that we've been doing with shales is been doing a lot of work on hydraulic fracture modelling. So currently, most geomechanical software isn't very good for modelling hydraulic fracture development. So we got, I think it was 12 different oil company sponsors, and I got a project set up with an industrial company that specialises in finite element modelling. And what we've been able to do there is develop a new software tool that models hydraulic fracture development from right at the start of developing the fracture, putting in proppant, cleaning up the fracture, and then modelling flow afterwards. And at the moment what we're doing is using this software for optimising fracture spacing, fracture sequencing, and whether or not to refracture. So this is just an example of it, where we've simulated 3 different hydraulic fractures in a naturally fractured reservoir. We model the stress in there, we model proppant transport